Hello, class. I wanted to make sure that I went through a couple of examples using the second derivative test for classifying points on a function of two variables as being local maxes, local mins, or saddle points. And so we remember what we did on Monday. We said the second derivative test was a way to classify those, and we said suppose that we've got a point where the gradient is equal to the zero vector. And really all that means is that the partial derivatives are both equal to 0 at that point. And then we defined this thing called the discriminant, and we said the discriminant is fxx times fyy minus the mixed partial derivative squared at the point AB. And all we really had to do is look at what happens to fxx and what happens to this discriminant, and we could determine whether or not a point is a local max or a local min. All right, so the first case was if the discriminant is positive and fxx is positive, right? And I think I told you guys that to remember this is suppose that the discriminant's positive, so the whole thing is greater than 0, and it's a product minus a square. Well, this thing over here has to always be positive, or that we're going to take away a positive number. So the only way that this could possibly be positive is if this product is also positive. So if fxx is positive, fyy has to also be positive. And if you think about what this means, fxx is positive, concave up in the x direction, concave up in the y direction. That's going to correspond to a local minimum, okay, like the bottom of a paraboloid. And then vice versa, if the discriminant's positive and fxx is negative, then fyy also has to be negative. Okay, there's no way that we can end up with a positive product unless this product is positive. All right, and so what happens is concave down in the x direction, concave down in the y direction. If it's concave down in both directions, that's going to correspond to a local maximum. All right, and then if this is negative, there's a couple ways this could happen to be negative, but one way is that if this is positive and this is negative, we're going to get a negative number minus a positive number is going to give me a negative result. And if we think about concave up in the x direction but concave down in the y direction, right, that's going to correspond to a saddle point. Okay, and then if d is equal to 0, this is one just to remember that there's no conclusion. That doesn't mean that it's not any of these, it just means that we can't make the decision based upon the second derivative test. Okay, so I want to go through a couple of examples, and the first one is one of the examples that I did in class, and I want to just go through this one again, and that is that f of x and y, suppose that this function takes on the value of, I think I did x squared plus y squared minus 4x minus 2y plus 8. And I think that in class we said a couple different ways that we could justify that there was a local minimum at the critical point. But to find the critical point, we need to find out what's fx and what's fy. Fx is going to be 2x minus 4, and we want that to be equal to 0. Fy is 2y minus 2, and we want that to be 0. This is going to happen at a critical point where x is equal to 2 and y is equal to 1. Okay, then all we have to do is find fxx, find fyy, and find fxy at this point, and then see what the discriminant is. So fxx is the derivative of this with respect to x is 2. Fyy is the derivative of this with respect to y, that's also 2. And then the mixed is going to give me 0. Either the derivative of this with respect to y or this with respect to x is going to be 0. So the discriminant is fxx 2, fyy 2 minus fxy squared. That's going to give me 4. So the discriminant is positive, and fxx evaluated at 2, 1 is equal to 2. That's also positive. So we are in the first case. Both of these are positive, which means that the critical point is going to correspond to a local minimum. So there's a local min at 2, 1. Okay? Um, I'd also like to take a look at justifying this graphically. So I've got this function put into GeoGebra, and what I'd like to look at is what happens in the contour diagram. Okay, so I've got this turned on so that over here at the point 2,1, we should see something happening as these levels increase. Okay, so if I increase the contours, right, there's not picking up anything there until we get to that point. Let's see, I think I've got the wrong one turned on, sorry. Turn that off, clear that out. We want this one on. Okay, and so I keep moving on this. What's it doing? Maybe I got the wrong definition here. X squared plus y squared minus 4x minus 2y equals z. Okay. And I think I need to, yeah, it's not turned on. All right, so let me go back to here and clear that. All right, so we're increasing the contours. X is 0. We're not picking up any part of the graph yet. There you see a point show up at the point 2,1. And then as we keep increasing, okay, these contours are getting bigger and bigger and bigger. There's z equals 7, z equals 8, z equals 9. So if you think about what this graph looks like, this is going to be a paraboloid with the vertex at the point 2,1, and it's opening upward as you move away from that point. Okay. If you think about what the gradients would look like on this thing, they're going to be perpendicular to these circles, so they're going to radiate out away from this point, and they're going to all be pointing outward. Right? So that's another thing that your homework asks you to do is sketch some of the gradients, and the gradients are just going to be radiating outward away from this point. Okay, so that was one of the problems that we had in class. I want to take a look at another one, and that was the one that looked like f of x and y was equal to x squared. I got a cheat here. X squared plus 4xy plus 5y squared was another one that we did in class. All right, so first of all, we want to find out where's the critical points. So find fx. Fx is 2x plus 4y. We want that to be 0. Fy is going to be 4x plus 10y. We want that to be equal to 0. And then in class we said x is equal to negative 2y. Okay, and then I plug that in down here, and we ended up with 4 times negative 2y plus 10y is equal to 0, or 2y is equal to 0, and we said y is 0, and when y is 0, x is also 0. All right, so there's a critical point at the origin, and then we want to classify it. So we need to look at what is fxx, what's fyy, and what is fxy. All right, so the derivative of this with respect to x is 2. The derivative of this with respect to y is 10. And the partial derivative of this with respect to y or this with respect to x, they're both 4. And so the discriminant is 2 times 10 minus 4 squared. That gives me 20 minus 16 is 4. The discriminant is positive, so we're going to be in case number 1 or case number 2, positive discriminant. But fxx is positive, so we're in the first case, and so there's going to be a local minimum at 0, 0. Okay, so let's take a look at that one also on GeoGebra. So let me turn this one on, and run that down to here. We'll get rid of everything. All right, we'll do the same thing. The z is going to be increasing. All right, you see a point show up at the origin there. There's a point at 0, 0, 0. And then when z is equal to 1, z equals 2, z equals 3, z equals 4, and so on. All right, ignore the circle over here. Just look at these ellipses. This is going to be looking down at kind of a squashed paraboloid that's been tilted a little bit. Okay, that's what the graph of that looks like. I can also take a look at the graph of this in 3 dimensions. And if we turn that one on, okay, you can see the graph here. If we tilt that a little bit, you can see that at the origin there seems to be a local minimum. And then if I rotate this way, and then we look down inside of this paraboloid, there's the contour diagram that you see. The very lowest point is going to be right here at the origin. It's a very minimum point on that graph. Okay? All right, so that's that second example. All right, the next example I want to look at is a little bit messier, and this function is f of x and y is equal to, let's do 12x squared minus 24xy plus 8y to the third power. Okay, 12x squared minus 24xy plus 8y to the third power. All right, and the first thing is we want to find out where are the critical points at. Okay, so the derivative with respect to x is 24x minus 24y, and we set that equal to 0. The derivative with respect to y is negative 24x plus 24y squared, and we want that to be equal to 0. Okay, so from this first equation, I think we can agree that x and y are going to be equal to each other. And then if we substitute down here into this equation, we're going to get negative 24y plus 24y squared is equal to 0. If I factor out a negative 24y, we'll be left with 1 and minus y is equal to 0, which tells me that y is equal to 0 or y is equal to 1. Alright, so when y is equal to 0, x is also going to be equal to 0, and when y is equal to 1, x is also equal to 1. So there's going to be one point at 0, 0, and there'll be another point at 1, 1. Okay, so what we need to do then is find out what are these points. Are they going to be local maxes, local mins, or saddle points? And to do that, we need to look at fxx, we need to look at fyy, and we need to look at fxy. fxx is 24. fyy is 48y. And the mixed is going to be negative 24. Okay, so at 0, 0, fxx is 24. At 0, 0, fyy is going to be 0, and fxy is negative 24. So if we look at the discriminant in this case, we're going to get that d is equal to 24 times 0 minus negative 24 squared. That's going to give me negative 24 squared, which is less than 0. Okay, so the discriminant's less than 0, and if we go back to our second derivative test, if the discriminant is negative, there's a saddle point at that critical point. Okay, so 0, 0 is a saddle point. All right, then if we look at 1, 1, fxx is still going to be 24. At 1, 1, fyy is going to be 48, and fxy is going to be negative 24. In this case, the discriminant is going to be 24 times 48 minus negative 24 squared. Okay, 24 times 48 is bigger than 24 squared, so I know that this is going to be positive. So the discriminant's positive and fxx is positive. That again corresponds to a local minimum. Okay, so this one, we've got a saddle point at the origin, and we've got a min at the point 1, 1. Okay, so let's see if that corresponds to what we can do with technology. All right, so let me get these shut off, turn this one on, clear that mess, clear that mess. All right, and so this is the contour of that function that we just looked at. It's 12x squared minus 24xy plus 8y to the third. And if we increase the contours, right, you can see there's z equals -5, -4, -3, and you start to see that circle show up at 1, 1. And if we increase the contours, we're going uphill now. So at 1, 1, there is like a divot there. And then when we get to z equals 0, we can see that there's something happening at the origin. We're increasing through the first quadrant and through the third quadrant, and then we're going to keep increasing into the second and fourth quadrants. And so hopefully you can see that there really is a saddle point there at the origin, and there's a local minimum at that point. Okay, let me run over that again. So here we're going uphill when you see these new contours show up, still climbing and still climbing. All right, saddle point here, minimum value at 1, 1. Okay. All right, let me go through one last problem with you. This is a function that we looked at before. It is e raised to the -x squared minus y squared. All right, so again, we want to find out where the critical points are, so we'll find fx. Fx is going to be e to the -x squared minus y squared using the chain rule times -2x. Fy is e to the -x squared minus y squared times -2y. And so we want to set these both equal to 0. And I think we're going to find that this is going to be equal to 1. I'm sorry, is going to be always positive. And then it's going to be dependent upon what happens here. So I think we can agree that there's going to be a critical point at 0, 0. Okay, no matter what you put in here for x and y, e raised to a power is going to be positive, so this is going to determine where the critical point is. All right, so as a critical point at 0, 0, now we want to decide is it a max, a min, or a saddle point. So we'll find fxx. Okay, so the derivative of this with respect to x is going to be an application of the product rule. The derivative of the first function is e to the -x squared minus y squared times the derivative of this, -2x, times the other function, -2x, plus the first function, e to the -x squared minus y squared, times the derivative of the second, which is -2. And then fyy is going to be very similar, be e to the -x squared minus y squared minus 2y times -2y plus e to the -x squared minus y squared times -2. And then the mixed is going to be the derivative. Let's do the derivative of this with respect to x. So it's going to be e to the -x squared minus y squared times -2x. And then this is just a constant, -2y, with respect to x. Okay, so again, we want to know what these are at 0, 0. So the discriminant is going to be what I get when I plug in 0, 0 into this expression. Well, these are both going to be 0 here. These are both 0 up here. E to the 0 is 1 times -2 is -2. Okay, if I plug 0, 0 in here, we're going to also get -2. And if I plug 0, 0 in here, we're going to get 0. All right, so the discriminant is equal to 4, which is positive, but fxx is -2, which is negative. So we've got a positive discriminant, negative fxx, where in the second case, that's going to correspond to a local maximum. All right, so if we take a look at the graphical interpretation of this, I'll go to my 3D grapher. And in my 3D grapher, I can graph that function. And this is one that we talked about the other day. So we said it looked like a pimple or something. And if you think, there's what it looks like, what's happening at the origin. There's a peak at the origin, right? It's the very highest point on the graph. And if we go back to here, we said there is a local max at 0, 0. Okay? All right, so that gives you a couple more examples to take a look at. This idea of classifying critical points as being local maxes or local mins or saddle points is something that is pretty important. It's about as important as being able to classify critical points in Calc 1. So this is something that is going to be pretty important to know. And this second derivative test is something that, however you decide to memorize it, it is something that needs to be memorized for quizzes and exams. All right, and I can guarantee there will be a question kind of like this on the quiz coming up on Friday. So enjoy your day off on Wednesday. You should be working on the next section, which is 15.1. You should be able to get through all the homework there in 15.1. And I'll take questions on that on Thursday. And we'll move on Thursday on to the next section. So, okay, enjoy your time off, and I will see you when I get back on Thursday. See you later. Bye.